Okay, guys, let's take a look at number 2. We have a bus, right? It's driving along the road. It has an initial velocity, right, of 20 meters per second. It is slowing, so the acceleration is in that direction. The V final, we're not sure what that is, okay? Oh, wait a second. We are sure. What does it say? Slows. It slows. Okay, yeah, we're just not sure. It's slowing. Okay, great. So we know that there's an FG equals mg down. We know there's an F normal. Those two are balanced. So if I'm going to sum all the forces in the y, then let's just make a box, right? So equality statement would be force normal equals Fg in the y, right? So if I want to do the forces in the x, we have some force traction, right? It's gripping, it is moving to the right. And what do we know? So there is some force traction, and I'm just going to tell you, it does not tell us. Yeah, I would say there's a force traction, and then I would say there's a braking force back this way. Yeah. All right, so if I do the sum of all the forces in the x, then I'm going to have force traction. I usually choose the direction it's already moving to be positive, so force traction minus force brake, right, equals F net. Okay, so whatever that is. Yeah. Okay, so if we come over here, we can see that I think I'm gonna try to have good markings on this. So 20 and 10 and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if I start at 20 and I slow by 4, I could count that out, and it should, it's not the perfect straight line, but so the slope here, so I should slow by 4 meters per second each second. 4 meters per second each second. Okay, well, how do I know to go to there? I sort of jumped the gun a little bit. If I come over here, it says well-labeled diagram, so we're getting these things here, make an annotated graph. You know, I often go to this part before I do the graph, which is exactly what I just did. So let's see, if I erase this right here just for a second, I'll leave the labels, and I come down here. How much time does it take the bus to stop? Well, if I want to know how much time, I can say V equals AT plus V naught. Let's think about it. When it comes to a stop, then the final velocity is 0. So I would say 0 equals 4 meters per second times what? How much time? T. We want to find T, right? Plus whatever our V initial was, which was 20 meters per second. Yeah. So let's see. How are we going to do this? So negative 20. If I add a negative 20 to each side, equals 4 meters per second times T. And here's the interesting thing. Oh, wait, it's meters per second squared. I hope you were screaming when you were hearing that. So since the acceleration is acting in the opposite direction, it has to be negative since it's opposing, right? When the sign of the velocity and the sign of the acceleration are opposing, then the object is slowing. So This needs to be negative here. That'll give me a negative 20 over a negative 4. We can see that the meters per second cancels out, right? And that is going to give me a second left over, right? So I'll end up with 5 seconds. When I say a second left over, I mean the unit. Yeah, so I think that's good. And then if I say starts at 20, goes for 4 seconds, goes for 5 seconds, right? So we didn't know initially, we just knew 4 meters per second, but now we're going to say that 5, I think I could have drawn that before just because I knew the slope, right? So I think what's important here is to see that, you see me kind of talking a little bit in circles, is that I could have found the answer to I, right, by saying I start at 20. If I come down to here, how much time does it take to stop? Well, if I started at 20 and made a slope of -4, then it would take me right there to 5 seconds, or I could solve it mathematically. So, okay, so that's good. So in all of these, I believe you can almost always solve almost all of it with, or big pieces of it with the graph or the math. Okay, so the next question is how far? So, I mean, how far is the area under this graph? So I could certainly just do 1/2 base times height. Or, let's see if there's another way I could do it. Well, my sort of go-to on how far is x equals 1/2 a t squared plus v naught t plus x naught. Right, so I appear to be starting from the origin, so I don't have an x naught. I do have a v naught, so 20 meters per second times what, 5 seconds is how long it goes. 1/2 4 meters per second squared times 5 seconds squared equals how far it goes. So how far indeed does it go? Okay, so I've made one really important error here that's going to really nuke me. That's a negative, right? So each one of these terms, this one, and this one, notice there's an x naught in there. Each one of these is a position. Okay, so that's obviously a position, x naught. V times t is a position. And then if we do meters per second squared times seconds squared, do you see that? That leaves us with position. So each one of these is a position. But if that acceleration is negative, then I'm going to end up with, let's see, 25, let's see, -50 plus, so it's a position, so meters, plus 100, a positive 100 meters, and so the x is going to equal 50. So here's the thing, if I hadn't caught that negative right there, then I would have ended up with 150 for my answer, which definitely would have been wrong. So net force, I started kind of to do it right over here. Net force, sum of F equals, I guess it'd be better to do that, what, we were doing it in purple for the X. So sum of F equals MA in the x, which is the only place we have an acceleration. So what's that, 5,000 kilograms times the acceleration is -4, yeah? So F net equals -20,000 newtons. Great, well done. Okay, let's see.